Hi Chem 101 students, and welcome to our last lecture on acids and bases. This lecture is going to be about buffers, and what you see on the screen here is a definition of buffer. A buffer is a solution that contains either a weak acid and a salt with its conjugate base, or a weak base and a salt with its conjugate acid that resists changes in pH. This resistance of changes in pH is extremely important to biological systems and your body, mainly because the proteins that do all the work for the chemical reactions required to produce energy for your body require a very strict pH range in order to function properly. And if your bodily fluids were to leave that range, it would cause big problems and very, very sudden death. And so we'll talk about what buffers are, and we'll also talk about some of the biological and medical applications to pH and buffers near the end of this lecture. What is in a buffer solution? Well, as I said, it's an acid and a salt containing its conjugate base, specifically a weak acid. It must be a weak acid because the operation of the buffer depends on the equilibrium that exists in weak acids and does not exist in strong acids. Also, we need a significant amount of both a weak acid and the conjugate base. And I say a salt with the conjugate base because the conjugate base is often going to be an ion. And you can't just go out and buy ions. They always come as a part of a neutral ionic compound or a salt. So the salt will contain other ions that are not important for the base, but are just there because they were a part of the salt. An example of this would be the weak acid nitrous acid and the salt KNO2. So KNO2 has potassium ions, but that's not really what we care about here. So KNO2 here, when it's in solution, as we saw when we talked about the hydrolysis of salts, it produces aqueous K+ ions, and it also produces nitrite ions. And it is the nitrite ions that we are interested in here, because the nitrite ion is the conjugate base of the weak acid nitrous acid. So if we have 0.1 molar of the nitrous acid and 0.1 molar of the potassium nitrite, or 0.1 molar of the nitrite ions, then we'll have a significant amount of the weak acid and its conjugate base. Note that nitrite is the conjugate base because it has one less proton than nitrous acid. No H, and the charge is down by 1 unit. Also possible is a weak base and a salt that contains its conjugate acid. Now, the only weak base that we talked about in this class is ammonia. That's the only weak base we're going to talk about in this class. A salt that contains its conjugate base would be a salt that contains ammonium ion. Again, here, ammonium chloride will hydrolyze into ammonium ions and chloride ions. And there are chloride ions there, but it's not the chloride ions that we actually care about. It's the ammonium ions, NH4+. And this is because ammonium ion is the conjugate acid of the weak base ammonia. It is ammonia with one more proton on it. It has an extra H+, see, extra H, and the charge is up by 1 unit, up from 0 up to -1. Okay. It cannot be a buffer if it has a strong acid or strong base in it. So a question I love to ask you guys is, multiple choice question on the final is, which of these mixtures of things would be a buffer? And it has to have a weak acid and its conjugate base, or a weak base and its conjugate acid. If it has a strong acid or strong base, it can't be a buffer. The reason is because a buffer resists change in pH by keeping an equilibrium. But strong acids and strong bases don't have an equilibrium, so they cannot behave as a part of a buffer. They do not have equilibria. So it must be a weak acid and its conjugate base, or a weak base and its conjugate acid. What does the buffer do? It maintains a constant pH when acid or base is added to it, which is really important. Let's say your body here, you drink a glass of orange juice or some lemonade, which is quite acidic. You wouldn't want your body contents now to become acidic. That would kill you. So fortunately, there's a buffer in your bodily fluids that is able to absorb this additional acid that has been added and not change in pH significantly. And the balance comes from the equilibrium, so it must be a weak acid again, or a weak base. How does the buffer maintain the pH at the same level? Well, the key component of the buffer is that it has a component that is acidic and a component that is basic. And so the acidic component can react with any base that is added to the solution and neutralize it. Also, the basic component in the buffer can react with any added acid and neutralize that. So whether acid or base is added to the buffer, there is something in the buffer that will neutralize it and keep the pH constant. So if we have a weak acid that's in equilibrium, like nitrous acid here, in equilibrium with the nitrite ion and a proton here. So this is its hydrolysis equation written without the water here. And we put a double arrow because there's an equilibrium. So a good buffer will have some of the weak acid and also some of the conjugate base. So it should have about equal amounts. So again, here the weak acid is nitrous acid, its conjugate base. What you would have with one less proton is NO2 minus 1. So it's going to be the nitrous acid, which is the acid part of the buffer, that will react to neutralize any base that is acid added to the buffer, so the pH won't change very much. And it will be the nitrite ion from the base, that will be the base here, the conjugate base of the acid, and that will react with any acid that is added to the buffer. So one thing that I also ask you to do, and I'll ask you to do on the homework, is to write the reaction of the acid part of the buffer reacting with base or with hydroxide, and to write the reaction of the base part of the buffer reacting with acid, also known as H+, right? So the acid part of the buffer reacts with the base, which we're going to represent with hydroxide. So we've got this buffer, it's got the weak acid, nitrous acid, and now we have added base to it. So remember what acids and bases are. Acids are proton donors. Bases are proton acceptors. And base, what represents a base in water is hydroxide. So the nitrous acid is the acid part of the buffer. It's going to give a proton to the added base, the added hydroxide, and that will neutralize the added base. What you'll get out of this is you'll get the conjugate base of the weak acid. So if you take one proton off the nitrous acid, it has no more H, and the charge goes down by 1 unit, from 0 down to -1. And then from the water, it's gaining it, or the hydroxide rather, it's gaining an H+. And so now there's going to be 2 hydrogens and 1 oxygen, and also the charge is up by 1 unit, from -1 up to 0. And so water is produced. So now you can see that the added base, the added hydroxide, was neutralized. And all you get is neutral water and more nitrite ions, which are already in the buffer. They're already part of the equilibrium with nitrous acid. The hydroxide ion concentration will not change much because it's used up by reacting with the acid part of the buffer. So no hydroxide concentration change, so no significant pH change. What about if we add acid to the buffer? Well then, and we're going to represent acid by H+1, or protons. Well then it's going to be the base part of the buffer that reacts with the acid. The base part of the buffer is the conjugate base nitrite ion. This is going to react with any added H+1, and then these are going, the H+1 will attach to the nitrous acid, and then we will get the nitrous acid back, the weak acid. So you can see this equilibrium that goes on here. uh, and so any added base reacts with the acid part of the buffer. Any added acid reacts with the base part of the buffer, in this case the nitrite ion, and thus the hydronium concentration here does not change very much, and so the pH will not change very much. So that's this idea written out in chemical equations. Note that the conjugate base is found as a part of the salt. So the salt, also, if you remember from our example, the salt was potassium nitrite. It hydrolyzes in water to produce potassium ions and nitrite ions, but the potassium ions weren't involved in any of these acid-base reactions. Only the nitrite ion is important because it's the conjugate base of the weak acid nitrous acid. Potassium is not involved in the reaction, so we call it a spectator ion. It's there, but it's not involved in the reaction. It's only there because you can't go get nitrite ions. You can't go buy any kind of ions. You can only buy neutral ionic compounds, and those are going to contain a positive ion, like potassium, that you don't need. What you really needed was the nitrite ion, and so you used a salt that contained that ion, and then potassium is the spectator. So when we've got this buffer was composed of the weak acid, nitrous acid, and the salt containing its conjugate base, potassium nitrite, which had both potassium ions and nitrite ions. So in this buffer, we've got the weak acid, nitrous acid, we've got its conjugate base, nitrite ions. We've also got potassium ions, but those are spectators. So here I've got a good buffer that has a good amount of both the weak acid, nitrous acid, that's represented by 4 of them here, and the weak base, and the conjugate base, nitrite ion. There are 4 of them there, and there are also 4 potassium ions. So now, what happens if we add some H plus to the buffer? Well, those H plus, some of them will attach themselves to the nitrite ion. So an H plus attaches itself to the nitrite ion, and you get HNO2. So by adding the acid, we have now 2 additional nitrous acids, but we still have 2 nitrite ions left. And so this buffer can still function. You could still add more H plus, and there would still be some nitrite ion to react with it. But there's less now. So a buffer does have a limit. You can only put so much acid before all the base is used up here. But now, because we added 2 H pluses, we have now 2 additional HNO2s. Now let's go back to the buffer before we've added any of it. Again, we're back to 4 nitrous acids and 4 nitrite ions. This time we're going to add hydroxide. And so the hydroxide actually reacts with the acid and takes an H plus off, and you get HOH, or water. And so notice the HNO2 was what react with the hydroxide, so we lost 2 of them. So we only now have 2 HNO2s, and we have 2 more nitrites. Now we have 6 of those, because when the HNO2 lost an H plus, it made nitrite. But again, this buffer is still usable. It still has more of the weak acid that could react with any added hydroxide or base. It still has the conjugate base, which could react with any acid. So that's kind of a visual picture of what's going on in the buffer with using, letters here. Now, in terms of our, so we said that a buffer could be a weak acid and its conjugate base. It could also be a weak base and its conjugate acid. But we only are going to talk about one weak base in this class. It's ammonia, NH3. And so its conjugate acid is going to be ammonium ion, NH4+. It's a conjugate acid because it has 1 more H plus than an H3. See, 1 more H, and the charge is 1 higher, from 0 up to +1. So here, the ammonia is the base part of the buffer, and the ammonium ion is the acid part of the buffer. So ammonia is a weak base. It's going to react with any added acid, added H plus, and that H plus will attach with ammonia and make ammonium ion. So notice we have 1 more H, and the charge goes up by 1, from 0 up to +1. So the base part, ammonia, will react with any added acid to a buffer that contains these 2. For the ammonium ion, it is the acid part of the buffer. It's a conjugate acid, so it will react with any added base. So if you add hydroxide, then ammonium ion will react with the base. It will be the acid. It will give the proton. The hydroxide will be the base. It will accept the proton. And so what you'll get is you'll get your ammonia back because the ammonium ion lost an H+, so now it's down one H and down one charge unit from +1 to 0. And the hydroxide now gains an H+, and that makes water. So remember, you can't go buy ammonium ions or any ions from the store. It would be a part of a ionic compound such as ammonium chloride, and with ammonium chloride, the chloride ions would be the spectator here. So let's do one more problem with one more buffer. Let's say we have a buffer with hypochlorous acid, HClO, and it also contains the salt sodium hypochlorite. What part of the buffer will react with the acid? It will be the base part. What is that? Write the chemical reaction for that. And what part of the buffer will react with any base that's added? Write the chemical reaction for that part. If you're watching this video, this is a good time to pause it. I'm going to explain to you the answer in a moment, but you've seen me do a couple of examples now. Why don't you try this one on your own? Pause the video and then start it up after this and see if you got it right. So pause now. Okay, I'm back. I'm going to show you the answer now. So oops, I kind of reversed these. These are often written both ways. I kind of messed up here. But I'm going to call, I call it HOCl, this should be HClO. Same thing, though, they mean the same thing. NaClO. Okay, there we go. So if we add acid, the acid is going to react with the base part of the buffer. Now, the base part of the buffer is the conjugate base. It's part of the salt. The salt has sodium ions, but the sodium ions are spectators. What we're interested in is the hypochlorite ion here. So that is the base part of the buffer. That's going to react with the acid. So if we have hypochlorite ion and H+, that's the acid that we added. This is the base part of the buffer. They react, the H+ attaches with the HClO, or with the Cl- and we get HClO. Notice it has an H and the charge goes up by 1 unit from -1 to 0. If we add base, it's going to be the acid part of the buffer that reacts with it. So our reactants here are the hypochlorous acid and hydroxide. So hydroxide's the base, hypochlorous acid is the weak acid. It's going to give its proton to the OH-, so when this loses the proton, it no longer has the H and the charge goes down by 1 from 0 down to -1. And the hydroxide gains a proton, so now it has 2 H's and the charge goes up by 1 unit from -1 up to 0. And that's how you write an equation for the reaction of buffers with either acid or base. And I've got problem 6 on your homework is about that, or one of the problems. This is something you need to be able to do. So why do we care? Why do we care so much about buffers? Well, if you're interested in living organisms, buffers are extremely important to the operation of living organisms. The blood's pH can range in humans from 7.35 to 7.45, and if it goes outside that pH range by 0.2 units even, this will mean death for a person. It's because you have jillions and jillions of proteins in your body that do all of the work of generating energy for your body, maintaining your body, repairing your body, all of these things, and they can only function in a very narrow pH range. If the blood goes outside that pH range, that causes the proteins to lose their special shape because they begin to react with the added protons or added hydronium ions, the extra, and then they don't function the way they're supposed to, and then your body can't make any energy and you die very quickly. And that's one of the reasons why when people stop breathing, they die as well, because that's important to the controlling of the pH of blood. In the blood, the buffer system is composed of carbonic acid and its conjugate base, bicarbonate ion. So carbonic acid is the weak acid in the buffer. The way you have carbonic acid in your blood is that it forms when carbon dioxide reacts with water. It makes carbonic acid. So we've all got carbonic acid to some extent in our blood, and that will react with any added base. So if we have carbonic acid and base is added to the blood, a proton will go from carbonic acid to the hydroxide, and so it will lose a proton, so the H will go down by 1. Also, the charge will go down by 1 from 0 down to -1. And the hydroxide here will take the H plus and it will make water. So the carbonic acid can neutralize any excess base added to the body in some way. And we'll talk about ways in which the body might become more acidic or basic in a moment. Bicarbonate ion is present in the blood. It can neutralize excess acid. It's the conjugate base of the carbonic acid. And so if we have bicarbonate in and more acidic components are being added to the blood, more H plus, it will react with that H plus and it will gain 1 H plus and make, so it will have an extra H here, 2 H's, and the charge goes up by 1 from -1 up to 0. And so in our blood buffer, carbonic acid is the acid part that reacts with added base. Bicarbonate ion is the base part that reacts with any added acid. And the bicarbonate blood keeps your blood in the right pH range for proper protein function, which is extremely important. So why might someone's blood begin to go outside the proper pH? There's a couple of what they call stresses on the pH of the blood or the body that could occur in various medical situations. One is a respiratory stress, so related to breathing. One condition is called respiratory acidosis. This occurs when someone is hypoventilating, meaning they're not breathing enough. So when we breathe, we not only breathe to intake oxygen, we also breathe out to release the excess carbon dioxide that is produced from our metabolism. And if we can't release that CO2, it begins to concentrate in the blood and it reacts with water and produces more and more carbonic acid, which causes the pH of our blood to go down and to become more acidic. So this can be caused by lung disease or by, just obstruction to the airway so that someone cannot breathe. Another condition related to breathing and the pH of the blood is respiratory alkalosis. Alkali is the other word for base. So it's saying, your blood becoming more basic due to a respiratory condition. This can happen in hyperventilation. So what you might have seen is someone's hyperventilating like that, and maybe in TV or something, you've seen them have them blow into a plastic or into a paper bag. And the idea is that by breathing into the paper bag, they're breathing back in more CO2 to keep the concentration of carbonic acid constant, so they're not losing all their CO2 too quickly. So hyperventilation can occur, of course, when someone is anxious or hysteric, and also if they have a fever. And so this can lead to an increase in the pH of the blood, which is a condition referred to as respiratory alkalosis. Metabolic stresses to the pH of the bodily fluids can also occur. One condition is called metabolic acidosis. This results in decreased bicarbonate ions in the blood, so you get more, you're losing the basic component of the buffer, so the blood is becoming more acidic. This can be caused by diabetes, either standard diabetes or very severe diabetes. Metabolic alkalosis is the opposite condition, where due to metabolic condition, the blood is becoming more basic, or the pH is getting higher. This is due to elevated bicarbonate ion concentration, so too much bicarbonate, too much of the basic part of the buffer, And this can be caused by vomiting or use of antacids. So when you vomit, you're vomiting up pH 1 to 2 hydrochloric acid that your body produces to help in the digestion of food. But if you are continuously vomiting, you're losing a lot of H plus, a lot of acid. So that results in a more alkaline body. Basically, you're missing acid, and so the body becomes more basic or more alkaline. Also, if you're ingesting antacids, again, you're putting more base into your body, so you're causing your body to become more basic, and that can result in elevated bicarbonate ion concentrations. So, you've been learning a lot about pH and acids and bases in this chapter, and maybe for those of you that are like, I just want to be a nurse or a doctor, you're probably wondering, why do I need to know about this? And it's because it's very important to the diagnosis and the understanding of certain medical conditions such as these. The maintenance of proper blood pH is extremely important, and it's important to understanding the way human bodies and other biological systems work. So that concludes the lectures on acids and bases. We've talked about the definitions of acids and bases and how to write hydrolysis equations for those acids and bases, the properties of acids and bases, pH and pOH, and also buffers. I hope this has been interesting for you, and I want to wish you good luck on your quiz. Make sure to see me in office hours if you have questions, and I will see you next time. Bye-bye.